it's my pleasure to introduce Pablo Ferrari, and he will talk. He didn't put a title, so he will talk to us a very nice problem.
So this is a fake. This is a fake first page. So no, I want to say some words for Antonio. That the first one is that we share many common interests, and one of them is Tai Chi Chuan. And Tai Chi Chuan is something that you do like that, right? Or like that. Okay. And the thing is that Antonio can do that while he's teaching, as you can see in this picture. So I couldn't do that. Okay, so well, so now I wanted to say that this room is historical for us because I came into this institute in 1977 in March. I was in the Master of Statistics, and then I did some courses with Vanderlei, who is here, and then in the second year, in the 78, Antonio gave a course of advanced probability, I guess. I was taking courses on probability, statistics, and research, operation research. And then, and I was already almost working with some other professor in operation research. And Antonio did something that is something that he does constantly. I would say that if he has a friend or a colleague and he thinks that are doing something bad or that his life should go in some direction, then he just say it. You should. That's so many people don't like that, right? I am the opposite. I say no. If he should do something, but his life. But Antonio is the opposite. So I thank Antonio for doing that with me at that time, because after that I started working in probability, and Antonio came one day and taught me duality in a table, I don't remember exactly where, and it's coupling and duality, and my master thesis under his direction is called the Wasserstein coupling and duality, I guess, for interacting particle systems. And then I did all my career essentially with these two things, and at some point, okay, I will not say much more than that, but at some point I got the musician, and we went to this serious place. What is it? We went to the Academia Brasileira de Ciências, and Antonio was already an academic, and that day, this was in 2011, and this picture shows also something that we had, and there's a lot of fun working together.
I tell you a story. Pablo was invited by the corretor de pesquisa because he knew it was famous. So Pablo arrived like this, and then he was dressed like us. But Pablo arrived like this. He said, you are Pablo Ferrari, the professor. Yes, that's me. So he starts speaking. He said, but you are Pablo Ferrari?
Who said that?
Corretor de pesquisa.
¿Quién era?
Corretor de pesquisa.
¿Era Armelín? No.
Não, o Pablo, você é professor titular?
Yeah, I am much younger than Antonio. Okay, so let me tell you about a couple of things that no. No. It doesn't work. ¿Está aprendiendo? This red thing is bad, right? Okay. So this is a joint work with Anna De Masi, that was also my colleague from many years, from 84. I met her. No, I met her before, but we started working together in 83 or 2. And Davide Gabrieli from L'Aquila, that he also came here as a postdoc many years ago and worked with Antonio and with me. There's old friends, both of them. Okay, so the title is Hidden Temperature in the Open Boundary KMP Model. The hidden temperature is, those that know what is hidden Markov chain, is a similar concept. And the KMP model, I will describe it now. KMP is for Kipnis, Marchioro, and Presutti. It's a model introduced in 82, I think, or maybe before, at the same time as this meta. It's a different thing that you have to look with different glasses. Yes. Yeah, this detail of the glasses is very nice from this picture. I like it. Okay, so let me put a setup. So we have a set of vertices. Bulk vertices are called V, boundary vertices are called B, and the closure is the bulk plus the boundary. And then I have oriented edges, and I write an edge. So it's a subset of the cross space, but I write just ij for the vertex, for the edge between the two nodes. So you can think the easiest graph that we can talk about will be this one. So you have n nodes, and 0 or n plus 1, 0 and n are boundary vertices. The black dots are bulk vertices, and I call I and j the vertices. And I will call B the vertices in the boundary. Okay? And then to this graph, I associate two fixed for all the talk temperatures that will call, well, it's n plus 1, this it seems. N plus 1 vertex, T0 and Tn plus 1, that we are interested in the case when they are different. And in this case, T0 will be smaller than Tn plus 1, but also we'll consider later at some point that they are equal to construct an auxiliary process. Okay, so to each, well, in this Congress, everybody knows at this point this kind of graphical construction, but let me introduce marked Poisson process that are calligraphic letters N, U, and B. And so N is the union. So N is a subset of R. Okay, it's a random subset of R. I think N as that. So it's the union of Nij, and I have for each bond or edge ij, I have a Poisson process that is represented by this losange here. Okay, and each, for instance, if this is point tau that belongs to the Poisson process associated to this edge, with tau come two random variables, one uniform in 0, 1, and the other exponential of parameter 1. Okay, so each event of the Poisson process has associated two random variables, and these are independent of everything. Everything is independent of everything. Okay, so the Poisson processes are independent, and the way I put these two marks is independent also of the positions of the taus. Okay, now I will describe the KMP dynamics. So I will describe the energy of the oscillator. This is the notation of Davide, right? So at the vertex, I have a value that is, say, I at time t. Said I of t is the energy of oscillator I at time t, and the vector z of t is is indexed by all the points in the graph, is governed, I will say that is governed by the Marquet-Poisson process and has boundary conditions T sub D. This is just the set, the vector indexed by V with the temperatures that were fixed at the beginning. Now I describe the dynamics for the bulk ij, so that means that both vertices I and j are in the bulk, and suppose that tau is an event of the Poisson process of the bond between these two sets, and u of tau will be the uniform random variable associated to that edge. And then suppose that I know the configuration at time just before the Poisson event, and I call z of I this configuration, the Poisson just before, and then let's call u the mark associated to point tau. So the dynamics is the following. So I put Zi represents the length or the energy of the oscillator I, and Zj in blue represents the energy of oscillator J, and they are interacting. When they interact, you just erase the boundary between the two and distribute uniformly in the segment. Okay, so the operation formally is you have your uniform random variable multiplied by Zi plus Zj and take a segment of this size, and associate it will be the value after the tau. And the remaining part is 1 minus u times the sum, and you associate this value to j. Okay. So this, as you can see, this is a conservative updating because I just moved so they redistributed the mass in a uniform way. And the interesting thing is that the way I choose this is independent of Zi and Zj, and also of the sum. The way the distribution does not depend on the configuration, how you distribute the sum. Okay, this will play an important role. Okay, in the boundary, I do the following. I have now two marks for the boundary because B is a boundary vertex, and I have a uniform mark and an exponential mark in this case. And then the bond I is bulk always because there are no bonds between boundary vertices, and then the bond I does the same as before. So the sum, you sum these two values and redistribute, and this is the part that corresponds to bond I. Okay, but the bond J, simply you erase whatever corresponds to it and replace by a new random variable that is the exponential random variable coming from the mark multiplied by the boundary condition TB. Okay, so you get an exponential random variable with parameter 1 over TB, right? So you, at all times you will have at the boundary an exponential random variable of parameter TB. No, there is an intermediate step here that you do the same as before. You do that, but then you erase this part. This you did before in the ball when both are ball, but when J is boundary, you do that. So I takes this part, but J says, okay, but I don't like this. I will take the fresh exponential, parameter 1 multiplied by the boundary condition, and get an exponential parameter 1 over non-conservative. Okay, so you will have two things, and the mass will flow from the right to the left. No, in the ball you don't use it. Yeah. Okay, so consider now the case equilibrium case. that there is no flux of energy or zero flux of energy. So I will, in this case, I take boundary conditions are equal to 1. So when you substitute in a time of a time when involving the boundary vertex B, but with an exponential of parameter 1. That, okay? And then if you take a product of exponential of parameter 1, is reversible for this process. And the proof is elementary, and is this line here. If you have two independent exponential 1 and you uniform and you partition that in this way, you get that u times xi plus xj and 1 minus u times xi plus xj are independent of exponential 1, right? This is an exercise in undergraduate thing, probably. Okay, and then this lemma is a bit more subtle because now recall that xi is the value of the associated to vertex I just before tau, and xj the same. So this is the proportion of mass corresponding to I with respect to the sum of xi plus xj, okay? And then I will call this variable d of t. And then I will have a d of tau. I will have a d of tau for each tau. But this, as you can see, this depends on the whole evolution of the equilibrium process from minus infinity to infinity in a stationary regime. So this lemma tells you that NV, calligraphic V, has the same law as NU. If you associate the uniforms corresponding to the previous thing, you get a collection of Poisson process, marked Poisson process with the same law as the uniform. This is, you can think and show it, but it's not totally immediate. But it's easy, the proof is easy. I mean, I can tell you something about the proof is that the configuration, and because you have this independence, no? You have that this V is independent of the configuration at time tau. And this is because, in fact, this Vt govern the reverse process. If you play the reverse process, you will have that x of tau, in fact, will be x star tau, that is the reverse process at that time. And this mark plays the role of u for the reverse. So it's independent under Poisson. Okay. Okay, the target today is to describe invariant measures for the non-homogeneous TB boundary conditions. In order to find the result, I need to introduce another model that is an opinion model with extremists. So I will call OI of t the opinion of individual I at time t. And an extremist is a vertex B that doesn't change opinion. So OB of tau is always TB. That is the same TB that we had before, no? And I will construct it as a function is governed by n and u, and it depends also on the initial condition, of course, no? The dynamics is very simple. When you have a tau involving sites I and j in the bulk, then OI and OJ are substituted by the same value. That is a value is a convex combination of the previous opinions, OI and OJ, and the convex combination is given by the random variable associated to the mark associated to the Poisson attempt. Okay, but OB, so the vertex B agrees with this procedure, but then at the moment that they have to change opinion, say, oh, no, I stay with opinion TV. Okay? So some people complain because this life is not like that, because people do not agree immediately like that. But in this opinion model, yes. Okay, so it's clear, this dynamics. Okay, so now I say, well.
So Pablo, excuse me.
Yep.
In this case, the model is on an undirected graph.
It's the same graph. Doesn't matter the direction.
Because before you said that if you have I with an arrow to J, then I changes, but not J.
No, only. No, before I have this situation, right? Ij, they are ordered, but I will be always bulk. The second, if I will write B if boundary, is J if it is bulk. Okay? The only reason that the bonds are oriented is because I need to know which of the two vertices will take U and which will be take Y minus U. Okay, I need to establish what is it, and this is the only reason why the bonds are ordered. The order doesn't matter, in fact. Okay, so opinion model is clear. I say, well, obviously this is a finite system. We'll have a unique invariant measure, but if you don't believe that I will perfect simulate it later. Yeah, but it's compact. Anyway, I will construct it with a perfect simulation scheme later. Okay, it's clear dynamics well. Okay, now the theorem is the following: is a paper. Yeah, with the temperatures of the other model. In this case, but you can have a general graph and with extremes in all the boundaries. Yes, exactly. Yes. And then, okay. So this is a paper with a theorem for the moment, because it's to be archived. So let me call O stat the law, the invariant measure for the opinion model with, so a configuration chosen with the invariant measure for the opinion model with boundary TV. And X stat will be the invariant measure for K and P with boundary 1. So it's product of geometric, of exponential 1. And then these two random vectors are independent. This is the hypothesis. And then define ZI stat, so the coordinate, the I coordinate, as the product of the coordinates, the opinion model times the exponential 1. So if you fix the opinion model, this is a product of exponentials of parameter of mean OI. Okay? Given OI, since they are independent, this is just a product measure with parameters OI. Okay, now just keep in mind that I will give you some pictures that will help you a lot to understand how this works. Now I claim, or the theorem says that if you call mu z the law of the vector with these coordinates, is invariant for K and P with the boundary TV. That is the same output here. Okay, so I have a description of the, and here you have another description that is more formal, but maybe it's easier to understand. For me, it's better this one, but this is also okay. So let's see, here is a test function. I am defining mu z. Then I choose the opinion vector O with the invariant measure for the opinion model. And then I choose exponentials, independent exponentials with parameter OI, the product of independent exponentials. Okay? So this is clear, it's obvious, no? That this phi is a test function. Test function.
It's like if you are conditioning on
If you condition on no, you have exponential, independent exponential with those parameters. But then here the O are the hidden temperatures. Because if you knew the temperature, then you know you have a product measure. But then you get a measure, but the O, they have is a configuration that has correlations, so these correlations you see in the thing. Okay, so that the measure should have this shape, I will give you at the end some background. Was already known since some years ago, because I will quote the paper, people computed the large deviation rates for this measure mu z, that they knew that there exists, and also Kipnis, Presutti, and Marchiori and Presutti already knew the existence of this measure, but they computed the rate function, and the rate function indicated, I am not an expert on that, indicated that the measure should be of this shape. It's like a mixture in some sense of it. Okay, so in order to do that, we found, or we looked for, and were lucky enough to find, a process, a coupling between the equilibrium KMP and the opinion model. So you realize with the same Poisson, no, with the same Poisson process, no, because there is something very subtle here, is that you realize the equilibrium KMP with the marks N, U, and B. But the opinion model, instead of realizing with U, the opinion model requires only N and the marks, the uniform marks. But instead of putting the uniform marks U, I put the uniform marks D that are in fact created by the equilibrium KMP model. Opinion model, no, because these B are exponentials that you use to substitute the value. TV, yes, TV, the opinion model has TV, but it's not governed by that, but you just keep TV fixed. Yeah, I should have put it here. So, yes, you're right. And boundary TV. Okay, so I recall what is V, this V here, are marks of this shape. No? So are marks that depend on the equilibrium model in this way. So the proposition says the following, that if x0 and the vector x0 and O0 are independent, then vector xt and vector ot are independent for each t. And I will not try to show this to you, but this is what we prove, and this is crucial, no? I try to say something here. You have you can think that these are the marks that govern the reverse process. So if this is like that, this mark is after tau for the reverse, because it's before tau for the advance. And then the configuration should be independent of this mark, because this mark appears as independent mark for the thing. In that case, probably yes. Yeah, well, this thing, I would guess so. Yes. Yeah, I would guess. I haven't thought about that, so I guess so. Okay, so this is the result here, and the second thing is more interesting, even because now I can couple the equilibrium KMP, the opinion model, and the non-equilibrium KMP in the same with the same marks. So vector x dot is the process. Equilibrium KMP governed by NUB. The opinion model is governed by NV. and boundary TV. And then Z of t is xi of t or I of t for each time, okay? I make the product of the coordinates. Then Z dot is k and p with boundary TV, the marginal distribution of Z dot, and is governed by any UB. And has initial configuration, the product, Hadamard product is called the thing I learned when writing this paper. Hadamard product of vectors. Okay, so I will try to show this theorem for you. It's easy because you can do it with a picture. So you have here x0, x1, x2, x3 that are exponentially independent of parameter R1. And the height here is the boundary conditions T1 at T4, say, yeah, of T3. And then Z is the area of these rectangles are x times TV. The area of these rectangles is exactly Z, right? Because it's the product of the opinion times the xi. Okay, so we stay in that Anna and David were looking at this picture, asking what do we do now? And that was not easy to find, but then we found the easiest possible solution, that is the following. You construct a rectangle of the same area as Z1 plus Z2. It turns out that this rectangle uses V for the height of this rectangle must be O1V plus O2 of 1 minus V. Because we are, sorry, I forgot to say that you have a mark that says that these two sides are interacting, right? And then that means that for these two sides, I have to put this point uniformly distributed in some of these places, but also for the Z, I need to do that. And then for the Z, to do that for the Z, you just have this new rectangle, that is this one, will have area Z1 plus Z2. This is magic. And then you have this situation. And then you're really happy because if you distribute uniformly the point here, it will be also, you will also distribute uniformly the volume, the area of the rectangle. And that tells you that that this dynamics realmente is a coupling between the two dynamics. Okay, I said you to do this in the boundary, but you could believe me that it works also in the boundary, okay? Here is what you do. The last. Okay, well, this is really nice, okay? But the problem is the following, that this opinion process, the invariant measure for the opinion process, we know how to compute explicitly only for n equal to 1. So this is reason. But we have more information. So this is a beta. Fabio showed me that this is a beta minus 1/2. And David calls this the arc-sine law. I don't know. Is it arc-sine law? Okay. So, okay. David computed it, but if not, you just can plug it in the generator equation and it's okay. Okay, but for n...
Well, the usual parameter is 1.
Minus 1/2. Oh, well, whatever, I don't, yeah. It's not minus 1/2. No, I think it's minus 1/2, minus 1/2.
Okay. X.
Half.
Arc-sine.
Arc-sine. Well, it is one, okay?
Yes.
But it's a transformation, right?
Yeah.
Okay. linear transformation. Well, okay, so now I will describe duality. The thing that Antonio 45 years ago taught me in that table. Okay, so for duality you have to consider a family of random walks, governed also. So because we have all these bridges here. This is the usual thing for duality. I take time like that. And you have associated to each one of these things a random variable v that is uniform in 0, 1. And then random one, but if you start here, for instance, so for each k and s, for each time k and s, you start a random walk that when arrives here, it stays at stays if this is k and if it's ig, no? It stays at I with probability v and goes to g with probability 1 minus v at j. Okay? So you start from here and then you can continue here or continue here with probability v, or if not, if this is I and this is j, and you have this v, then you continue here with probability 1 minus v and go here with probability v. But if you have two walks, you have one that's coming here and choosing v, the other walks does the same because they coalesce. Okay? This is what is saying here. And for that, I need a new uniform random variable u prime that you compare with this v to know if you go to if it is less, you go to here, that will be with probability v. And if it is bigger than v, then you go up in the other direction. Okay, it's clear. But you have a huge collection because you have for each s, you have a random walk starting.
Directed from one point to the other one.
Yeah, it's directed because this is I and this is j.
It's not from I to J.
From I to j. But this is metric, no? Because you have another mark from. You have another mark. The I will behave like j, say. But the law for j and for I is the same. At rate. If you integrate all the mass, everything, you have just coalescing random walks. And symmetric random walk that jump with rate 1 and the nearest neighbor to the right, rate 1 nearest neighbor to the left, and then they coalesce. And then they are absorbed at the boundary. Okay, this is a boundary thing, the bound doesn't go to the left. Clear the collection well. Here is my picture again. Okay, but as I said, no, so if you could just integrate everything, you have random walk, symmetric random, coalescing random walks. No, nothing interesting there. But if you fix the n, the Poisson marks, the Poisson events, and the v marks, then you have a random walk in a space-time random environment, right? Because you arrive here, this mark is here, you have to jump here. And if another process comes, they will jump here, all will jump with the same v. So all have a drift in one of the two directions, okay? And then you have a proposition that is a classic proposition for this kind of thing, that is a duality formula for the opinion model that is the following. Suppose that S is bigger than 0, and you have the opinion model governed by NV with initial condition O, and R is a family, all the family, the random walks governed by N d and u prime is to decide where you jump. And then you have that the position, so the opinion model at time s, you can express as the opinion or the random walk started at s at position I at time 0, so you are going backwards in time. So s is here. So now s, this is here. I have opinion 0 here. So the opinion of this guy I here will be, well, I take all the random walk, that's something like that, but what I have to take is the expected value of the opinion of maybe this is thing. So this is the probability that a random walk starting at S at site E at time 0 is in J. Okay? Given the marks, given all the marks. So the Poisson process and the V marks are frozen. And then if you arrive there, so you get the opinion OJ of 0 weighted by this random weight. This random weight depends on the Poisson process. Okay? I think these two formulas are the same, but this is clear. It's for me, yeah, omega here is N and D. Yeah, because I am integrating over U prime. Yep. I integrated over the jump. And then you get something that, you get weights, random weights, that sum 1, that are this probability, at time 0. And then these ways you get the opinion at time 0. But if you go further, so if you erase time 0 here, and you go further, you will eventually be absorbed at the boundaries. And then in this way you can simulate or construct the invariant measure, because I define O stat in this way. You know that you will be absorbed at some point in the boundary. So I call theta is the absorbing time of the walk started at S, at I, at time S, and then it's going backwards in time. Then will be absorbed at this time at some point in the boundary. So this point will belong to the boundary. And then I take, with this weight, I take temperature TV. Okay? Okay, and then I define an opinion that this is random weight, random convex combination of the boundary opinions. And this opinion I call O stat, and the vector O stat is invariant for O. And then, okay, so you bought me without explanation that this satisfies the dynamics, no? Okay, so this is just an exercise in here. With that, is immediate to do it. Okay, so my time is what time I should finish in 35 minutes. I have, right? Okay. Okay. So this is my present for Antonio's birthday. So now you take the opinion model that we don't know, because the opinion model has invariant measure is something like that. I don't know. No, it's maybe like that, and then like that, say. The typical configuration, you have some pairs some pairs of opinions are the same because they agreed at some point, and some other pairs are different, okay? Okay, so I define now the indicator function of difference, of disagreement. So I take the opinion model, an evolution opinion model, and then I define dij, this is associated to edge ij, is 1 if the opinions disagree. And so D, if I put D here will be 1, 0, 1, 1, 1, 0, 1, okay? For this configuration. Because here they agree and the other points disagree. Okay? And it's funny because the evolution is the following. If I decide, for instance, that this vertex will agree, let's say, this one, so let's say that this is ij, and they decide to agree. So they will find an intermediate point here and will agree, right, at this point. So this means that the ones that were agreeing before, this one that was 0, then will become 1. So after the thing, this will become 1. I get 0 here, and I will get a 1 here. Okay. Okay, so it's a spiking model without, it's our spiking model without rate of leakage, without leakage. The nice thing of this disagreement process is that it is Markov, each coordinate is Markov alone. And so you can do a perfect simulation of that. The other thing here, this is a perfect simulation of the invariant measure, right? I forgot to mention. You can do a perfect simulation because if you know, so you are using these same marks, no, to do the thing. So if you go at time, so you start you have a B0 here, but 0, 1. No. At the boundary it's always 1. Suppose that you have a situation like that. Then you know, for instance, that at this point, when this mark appears here, these two guys will agree. No, the 0, 1, like that. Sorry. 0, 1, 1. You have something like that. You cannot have two zeros neighboring, yeah, you cannot have. And then if you go backwards in that direction, it is enough to visit all points to construct the invariant measure. And this is what I am doing there. You take a permutation of the sides, because you only need, because once that you pass here, you know that here will be a 0. 2 will be 1. And then when you come here, you know that here will be 0. And this will be 1. Okay, you finish already the simulation with these two marks. Okay? And I did there a manual simulation and explained how it works. I have no more time.
Can you come again? You are going this way. You are doing perfect simulation on this.
I am doing perfect simulation. So when you have a mark, okay, the two opinions will agree. So if you were 1 here, that corresponds to one situation like that, then both of them will agree. And the neighbors, if they agreed before, they will disagree. If they disagree, will still disagree. So if you, after this mark, you know that will be a 0 here and 1, 1 here. And then you go backwards and you find this mark, and you know that after this mark, you will have 0 here and 1, 1 here, and then nothing that happened before will matter. So you do the perfect simulation like that. I wrote it down in that case, because I put, I have a, they are 8 bonds, 9 vertices, 8 bonds. And then in this line, there is a permutation of the bonds. Okay? Just to say which is the first bond to interact, but this I am looking backwards in time here. And then you have the first one will be 1, so I put 0, 1, 0. These are the dots are not decided yet. And then the second one is this one, so I put I cannot touch what happened with the 1, so I should put 1, 0, 1, 1, okay? But this one were already put, so I don't touch this one, I just add this one. Then comes the third. I have to put a 1 here. I should put a 0 here, but no, I should put a 0 here, but this boundary vertex doesn't change. So I just put a 1 here, and then the 4 is here. I don't know, was already, I cannot do anything because was already plain. And then the last one is this 1, 5, I put 0, 1, and here. So this is a perfect simulation. And you see that you don't depend of anything. If you when you visited all sites, no. I only go back. Back in time. Yes. Or you can just, you have to find the first time that you have a mark for each one of the sides. This is.
Why in the A2 you put a 1?
No, in the boundary are always 1.
The A2, why you put a 1 in the 4?
Eta 2 corresponds to this. To this side. I should put a 0, 1 here and 1, but these were already occupied, so I don't touch them.
Okay, but if you try to put a 0, you cannot, but then you have to put a 1.
Yeah, you put the 1. Anyway. Because this is something that happened before, right? It's like if something that happened here. You put a 0 here and 1, but then this one killed the 2. Okay, so this is for Renato. You can this spiking process is a Brownian wave if you consider it in R, because this thing works in any graph, right? I am okay. And this, well, I will steal 2 minutes because I like very much that. So you can have discrete KNP process. That means that you, instead of having a real number, you have a natural number or 0. And you have a uniform partition also. You choose a play or 0. No, you have 1, 2, 3, 4. You have to choose a boundary here uniformly, right? And you have n+1 sides, right? If you have 4 balls, you have to divide uniformly between the two things. You have to choose uniformly one of these 5 edges. So I will use the following lemma that constructs a coupling between exponentials and geometrics with the same means using a Poisson process. And then suppose that Z1, Z2, Z3, Z4 are exponential random variables and independent. And then run a Poisson process in this segment, occupying Z1 up to Z4, and count the number of balls in each segment. Okay, and then exercise. These are independent geometrics with the same mean as the exponentials. Okay, and then it's clear, no, that's exponential because you go from here to here and you see you have some probability to find a ball or this well, this is an exponential one. Or this thing, well, this is exponential, right? So you have the minimal between two exponentials, and either you get this or this, and then starting from here, since this was exponential, and from here this is still exponential, so the next one will be the boundary or the new ball, etc. So, so you can, it's a proof that in fact. Okay, so here is the proof. No, now I just how you couple the you couple the dynamics now. You have your couplet configuration of balls and the geometrics and exponentials. Then I want to iterate this point here. So I erase this point and put it, erase this point and take the balls in these two sides and mix uniformly in the interval, in the union of the two intervals. Okay? This is the Poisson process. So these are just 3 uniform random variables in this interval. And then now I put another random variable with the same distribution that is the boundary. So the boundary will have the same probability to be here, 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 and here, or here. Okay? It has the same probability of being any of the order statistics. So at the same time, I did the dynamics for the continuous KMP and for the discrete one. So I'm almost finished. In the boundary, you add this new Poisson process here. But okay. When I finish here, that's just a background. Kibnis, Marcuero, Presutti was the original paper in the 80s, and then Bertini, Gabrieli, Leibovitz later. I should have put the years here. And here they computed the large deviation rate functional, and also the paper Bertini, De Soli, Gabrieli, Giornalassini, Landini. And this was the starting point of this work. Then the invariant measures as mixtures of product measures. There are several papers. Derrida, I think, it also realized that. And there is a recent paper by Carinci, Franceschini, Gabrieli, Giardinà, Zacarios, Giannis, who prove a result similar to ours for the zero range. And the opinion model, there is a huge bibliography. I took just a couple of mathematical papers, and one of them is called the gossip model, that is more similar to us, that the two individuals, they agree at the middle of their opinions instead of a random place. But they study other things. They study the convergence to what is to consensus. Normally, these processes converge to consensus, but the Fuyuan, they invented that if you disagree a lot with someone, then you don't take him in consideration and you then don't interact with that. And then in that case, you can have consensus, divided consensus. You have a microscopic block of people with one opinion and another microscopic block with another opinion. Things like that. Eh? Like the famous Grieta, that is not that, right? Because okay. Yeah, and then the spiking process is our spiking process is just a version, ultra simplified version of the CGL model, and also of a model that we were working with Galves and Locherbach and Grigorescu. Okay, thank you.
Any questions?
I was just wondering about the opinion process. If I understood well, you're looking at the backward random walk, right? So
Yeah.
would there be any use for looking at the forward random walk where you have some perhaps materiality properties?
I will look at that.
Because it looks a bit like the rock.
No, it looks a lot. I will do that, yes. But so in principle, we should be able to compute these covariances. For the backwards, I don't know. The forwards is the same. No? Yeah.
More questions?
This backwards, to remind the state, you just see where it gets out in the boundary.
Yeah.
You suggest there is some uniquity, harmonic function in Laplace eventually.
Well, it's a harmonic function for the given environment. It's a harmonic function, I guess. Yes, I'm not sure. No, yeah, but you see that you change your. If the V would be the same for all things, would be a harmonic, but here you are changing the V also, so it's not clear. But for the integrated thing, you get exactly the harmonic function for the expectations. For the expectations, you get the harmonic function for the random walk. Right? Yeah. Yes. But this is the answer is yes. Thanks.
Excuse me, Pablo. V is always the one-dimensional lattice, or no?
Not necessarily. No. Any graph.
Also the process V?
See also that. Yes.
Because the constraint you have for a general graph about the V.
The D is just the difference between two neighbors.
But
You look at the difference.
if you have a triangle, then you have too much.
No. No, you have different. You have a graph like that. Well, say like that. Doesn't matter. Any graph. Eh? So D is associated to the bond.
Yeah.
So you have an opinion here and an opinion here. If they are different, D is 1. If they are the same, D is 0. So when you put the 0 here, you have to put the 1 in all neighbors. If you have 0 here, then all this must be 1. Unless you started with all ones. No?
More questions?
See, like this reminds me of the paper with vigorous on
Yeah. It's the same. But there the invariant measure was easier because you have.
But the dual with what that is not the same.
Yeah, the dual was because the dual for the is much simpler. The dual for the differences.
Which one? The one with expectation?
The one for D for the differences.
After difference.
For the difference, this is much simpler. Because you can just simulate in a few steps, and it's Markovian. The marginal is Markovian. But this gives you some information.
The cloud is not Markovian.
Hmm?
The paper by vigorous on cloud
Yes.
is not Markovian.
Probably yes. It's the same. Yes, should be. Yeah. Yes, because you get a 0 and put ones in the thing. But then you have a spontaneous 0, right?
You have spontaneous
Yeah.
negation. you have the two effects, leakage and sparking.
Yeah, but both of them are Markovian. No, well, yes, both of them are Markovian. So, well, not sure. No, because no, I'm not sure because because here you have ones that you don't move, and this helps you to be Markovian. Yeah. And if you put the 0, I think then you will get.
You move the one with either because it's 5 or because you die.
Yeah, but yeah, I should look to this one.
More questions? Okay, let's say video rules first.
No, let me thank the organizer because I am the last speaker. So thank you.
Let me say a few words, but I'm very happy to see this event as a reality. The original idea came like 5 years ago. It was a joint idea, Florencia Leonardi, Sandro Gallo, and myself. And we came to Antonio with the volunteer to do this event, and then he answered that no, this is a methodological event.
I said, well, why not? If you discuss the recent papers of mine, I would be very glad. So it's appeared.
Yes, I was going to say that. He said, okay, let's do a neuromap event. Well, we didn't arrive at a final idea, a final shape for the event, and then came the pandemic, and then time passed away. Unfortunately, came Claudio Landin with the idea, and Professor Antonio to make the school, and now this is a reality, and I hope Antonio enjoyed and look and feels as the school as a celebration of life and all of his achievements for future collaborations and friendships. Okay, and I want to thank all the participants for being part of this event. And I also want to especially thank in second place, there's Antonio, but in second place, this event would not be possible without the help of Lourdes and Maria Lucia, were fundamental for all the organization, the secretaries, and also the secretaries in Rio de Janeiro, Limpa, Lee, Leticia, Thais, and Ricardo. So thanks to everyone. And see you in the next week. Well, I don't know if I can say it. Okay.
No, the next school, if we know that the next school is probably in Bahia, the next school is going to be in Salvador, Bahia. Huh?
Almost surely.